batch process optimization, BASF polymerization reactor presentation. I am Chuck Wilcox, a project engineer with BASF. We'll also have Jason Garkey, operations engineer at Greenville. Ted Matsko will be doing some talking a little bit later, and Tim Mast is here for technical support for Ted. Last year's Automation World in Orlando, I put my name in one of the fish bowls that said free fingerprint analysis. Guess what? I won. And the results of that fingerprint analysis is actually what the rest of this story is about.
So this slide just kind of summarizes the project. The who is BASF and ABB. In particular, it's ABB Optimization Services. All right. The what is we want to improve the batch cycle time. That's really the goal here. The one in the where we're covered already. The why really has to do, it's not related to batch in any way. We always, every project I'm involved is we're either looking at improving yield or increasing production rate. Because when we're involved in advanced control, it's always tied to some economics. Because you've got a control system, it's working, at least to some extent, and if you're going to hire us to come in to do something else, we've got to improve things in some way. So now, batch is a little different in that in a lot of big chemical plants, refineries, one of the big sticks for economics is increasing production rate. All right. Well, on batch, production rate really means cycle time. So we're going to see that our tools focus in on cycle time somewhat. So, and that's what most of this presentation is about, is how we applied the tools to achieve that end. We used 4 different tools in this project. They are all supplied by the group that Tim Mast works for. The first was a Harmony scan, which really isn't related to the process. It's related to the DCS. And it's a new service that ABB offers. Alec Viloff is sitting in the back. Can you raise your hand, please? Thank you. He is responsible for going out and doing these fingerprint studies. This one's called Harmony because that's their DCS. It is a Harmony DCS, but we do it for other DCSs as well. He is down in the service booth right next to me, so if you want to learn more about that, you can stop and see them. Then we used, for data collection, we used a tool called the Data Logger. That's a tool that's been around the Optimization Services group for a long time. It's been used for many years. It's a really handy tool that will collect data through OPC. It has some really powerful features for triggering, and instead of collecting data 24/7 like you would with a historian, it collects the data you want when you need it. And it collects it usually at a little higher frequency with no compression. So it's some pretty important features for us when we want to analyze things. And the new tool that we use is the Sequence Analyzer. And we have another package called the Loop Analyzer. It looks at control loop performance. We do have some continuous control loops in the batch. Obviously, they don't operate after the batch is done or before the batch starts, but during that period of the batch operation, we do have some periods of continuous control. And we did find some problems there, and we use the Loop Analyzer to look at a couple problems there as well. This is an ongoing development project where we've added features as we've gone along during this project. We still want to add some more features. A couple of things that we will do is we're going to enhance the ability for multi-line support. Right now the tool will support multiple lines, but it requires the engineer to be smart about the way he sets up the data structures. And we want to make that easy. We're going to add user-defined calculated points. I think that's probably already in the tool. I just don't have that version yet. And then we're going to add some regression analysis, which you can see that I used later in the presentation.
Thank you, Ted. Why are we here, or why are we optimizing this? That's, I think, a base question. What were we making that needed the improvement? In this particular reactor, we were making what's called a polyester, and this is from the BASF external website, and this is a really good example of what polyester in action looks like. You mix 2 components together, and as they start reacting, you have the benefit of flexibility. As you notice, the polyester begins to form, and it takes the shape of the container or whatever mold that you might have. And once it's free, it freely expands to a larger volume. So it does a very good job of expanding. It's used, polyesters are used everywhere. BASF, we have very different flavors of polyesters. You have all kinds of things that you can do to give it better thermo-oxidative resistance. You can kind of custom design the molecule to meet the needs. This is a functional solution that BASF provides. And we have, in Greenville, we have what we call the I reactor. The first part of the plant was labeled alphabetically for their reactor trains. The later part was labeled numerically. But here we're talking about making a polyester in our Greenville, Ohio site I reactor. And it's made by a solvent process in a batch reactor. This is a batch process, followed by a fractionating column to remove trace amounts of water. The processing time was unacceptably long, had too much variability, and that's why we needed some additional assistance to provide a solution. So briefly, I'm going to go over the chemistry so that there's a little bit of understanding of some of the problems and benefits of the chemistry and when things don't go right. So there's a little bit of an understanding and background to why Ted's analysis really helped out. For a polyester reaction, you start out with an acid monomer, and the box in there could be any chain length. There could be any number of things in there, but what's important is the carboxylic acid functional group at the end, and also another one there. And then your other reactant is alcohol monomer, a diol, glycol. Again, the box could be many things in between. That's where the customization comes in. But the functional group is the hydroxyl group at the very end. And what goes on is that these two, in the right circumstances, these two reactants will work together, and they decide, we're going to get together, we're going to make something better here. And this is what's called a condensation reaction. What that means is the two molecules will join together, and as a result, they will liberate a smaller molecule after they are joined together. In this case, once they react, they form water. And that's actually a very good thing, because this makes this overall reaction much less hazardous. We have acrylic reactors at the site. That's very exothermic. There's a lot of safety instrumented systems that need to be in place to make sure we manage the risk appropriately. We are certainly willing to take risks as long as we can manage them and control that. Whereas here, this is a much less hazardous, much easier reaction to deal with. It's a slower reaction than acrylics. It's also endothermic, so we have to supply heat to make this reaction go. And typically we'll have this at 385 to 450 degrees Fahrenheit during the batch. The end result is what we create is called a polyester. Many esters are made as a result of this reaction. So once we've reacted, we've made the polyester molecule. And okay, how do we measure the process? How do we know that things are going right or things have gone horribly wrong? We have to have a way to measure that. In the polyester molecule, we again have the carboxylic acid functional group. We have the hydroxyl group at the end, and somewhere in between, we have the ester linkage. It's one molecule, but we have what's called an acid number test. It's a relatively common industry test. Starting out, we had a monomer acid, so therefore we have a theoretical expectation of what the acid number is starting out. When we're done, assuming a certain yield and batch processing time, we have an expected endpoint for the acid number. It's a little bit of a measure of what's left and how much what's left is going to be what's reacted onto the side of the overall molecule if everything goes right. We have a test for the hydroxyl functional group at the tail end of the molecule. That's a pretty basic test. It used to be done through wet test methods, wet chemistry on the bench top. Nowadays, we've advanced to the point where we can do it through near-infrared analysis. It's much quicker, very simple way to do it. It makes getting results much faster. Near-infrared, otherwise known as near-IR, NIR. Then, if everything goes right at the center of the molecule, we really hope to get within a certain target viscosity range. If we deviate too far on our viscosity, that could be a sign that perhaps instead of forming something like this, we've ended up having some dysfunctional chemistry going on, and we'll have viscosity growth, and then that really becomes off-spec. Really, this is a very robust chemistry. It's kind of hard to screw up in a lot of respects, but if something does go wrong, it is fairly forgiving. Typically, the price you will pay if you don't do this right is typically you'll either have your acid number out of line or your hydroxyl number out of line, And it costs you time. And eventually, okay, fine. Maybe if the reactor is not fully utilized, we can maybe give the time. But it really gets to be a point where if you abuse it for too long, eventually bad chemistries will go on with the center of the molecule, and then that makes it much more hard to recover. The equipment involved in this chemistry. We have a batch reactor. That's where all the primary reaction happens. We load all of our reactants, the two primary reactants in there. And we have an oil heating system to bring it up to temperature to make the conditions right for the reaction to happen. We have an oil control loop. That's an inner loop. And then we have a batch cascade control loop where we can set the temperature of the batch reactor and have the internal oil loop do what it needs to do to warm the reactor up to the desired temperature, and do it in certain ways with certain limitations. Once the reaction is going in the reactor, we have a fractionator that, as I indicated on one of the previous slides, we generate a lot of water in this reaction. Part of the trick is we want to make sure that we are preventing the reactants from going out. We want the water to leave because this is a reversible reaction. If we do this wrong, or if the water stays in, we're going to take 2 steps forward, 1 step back, and that's going to cost time and quality. So we will then go through a fractionator column, which has its own settings that are critical, because if too hot, well, then we're going to start losing reactant. Too cold, water may end up falling back into the reactor, and then that's going to reverse the reaction, 2 steps forward, 1 step back. So balancing the energy between these two and the mass generated of the water is really critical, because once we're past the fractionator, that's the point of no return. We have passed the Rubicon, and we have the condenser, which will condense everything that goes to it, and then it will end up going to our decanter. Once it's there, it's done, it's out of the system. We don't want to return it to the reactor. That would be a very large step backwards. So it's very important that we control here, because everything here is passive. Okay, so that's the front end. Operators can click buttons and make valves move and turn agitators and pumps, but to really take advantage of automation, we have, as Chuck indicated, Process Portal B, SimBatch, Produce IT, as it's known. And in our applications, typically our site, we're at 96 to 98% automated with SimBatch capable systems. And that's part of Chuck's justification for Chuck's project, so that our older reactors can be made SimBatch capable, Produce IT capable. Typically in our reactors where we have introduced Produce IT SimBatch automation on the top level, we have greatly reduced our variability and improved our cycle times, made things much more consistent on the quality end. However, the batch cycle times on this particular reactor and this particular chemistry, we became a little bit more accurate, but I would say we were not as precise as we should have been. We were definitely seeing anywhere from 5 to 10 hour variations, depending on how many times we had to resample. This reactor was running full out. What the business case was, do we want to run on a 7-day operation or a 5-day operation? How much capital money do we need to invest to stay at the 5-day a week operation? So if we don't have to invest the capital money to just get more out of our existing equipment, that's really the way to go. So when the SimBatch route didn't quite get us there, we were working a lot of overtime. We formed a multifunctional team of chemists, operators, engineers, operations management, and we identified areas for improvement. Really forming this team to ask a lot of questions. What do we think we know that maybe is not right? What's not working that we do know about? What can we do about it? So we were continually making improvements as we went along in this process. But as Chuck indicated, we won the fingerprint report from last year, Automation World, and ABB offered this tool to help us out. They were looking for a great test case, and that's where I think Ted comes in.
We had already been developing this tool. It was not being developed for batch specifically. Its original use was in pulp and paper application, but we knew that it would be useful in many, many industries. So we knew that batch chemical especially, there certainly are applications in Other industries that have grade changes like continuous polymerization, and even in utility boilers that run base load at night, they ramp it all the way back, and in the morning they ramp it up to full load and they run full load all day. That's another place where they're real concerned about ramp rates, where we could apply this tool as well. Jason showed you the graphic of the reactor. There are 6 control loops on that reactor. There is a hot oil temperature, and that's cascaded to the reactor temperature loop. It's a little bit complicated because there is also an override there that I didn't know about at first, and that is active during one of the steps, and that keeps the delta T between the coils and the reactor within a certain limit, so that limits how fast you can heat, so that does affect the step time. There is a condenser overhead, and we can do an energy balancer on that and calculate the water flow. That loop's not in use. If it was in use, it would be cascaded to the same hot oil temperature. There's a fractionator overhead temperature loop, which is very important, and there's a reactor pressure loop as well, which we found saturates during the vacuum operation of this reactor. So the main conclusions are we found oscillations in the reactor temperature and the fractionator temperature, so we'll look at those next. The hot oil loop override was active, and it did saturate near the end of step 3. So that does slow things down as well, and there is some corrective action that could be taken to possibly eliminate that saturation. And the pressure loop saturates was just a different story. So we'll talk a good bit about the vacuum and how that affects the batch cycle time. Here we have a typical set of data from a batch. This is the fractionator temperature, and this is the reactor temperature. So you can see as the reactor is heating up, the fractionator temperature jumps like 100 degrees. That's when the reaction starts and all that water starts being driven off overhead. In this particular example, I have a batch here that had a long delay, and we'll see later how we can deal with that type of event. But we want to focus first on the temperature control way up here where you really can't see anything happening, all right? So that's the first place we're going to use the tool, is we're going to define, this is the tool that we use, this is called the sequence analyzer. We're going to define some steps for the batch, all right? So I've got some logic here that you can't read, but it's related to either some solenoid valves or reaching some temperature limits. And there were 4 steps that were defined. There were steps 2 through 5 because step 1 occurred really before the reaction really started. There really wasn't anything electronic that we could key off for that. That was more the operator getting ready to start the batch. So that's step 3 right there. And let's see what happens when we zoom in on the data. This is step 3 and that's step 4 for the same sets of batches that we're looking at here. And the first thing we'll notice is that the overhead temperature during step 3 shows some oscillations. So let's zoom in on that. They're actually quite severe and rather rapid rises in them. That might mean that it could be stiction. It could also possibly be that it's could be a tuning issue, because we're tuning this controller probably for this rapid rise. And once we get up to temperature, this seems like it's really small, and well, you can see on that scale it doesn't seem to matter, but it does, because each time we hit one of those peaks, we lose one of the monomers out the distillation column, and that's lost money. Plus, it affects the reaction, and that means that's going to be lost time, because that's going to mean you're off spec, and you're going to have to correct it later on in the batch. The second condition we're looking at here is the oscillation of the reactor temperature. And that again doesn't seem too bad. We go up this long ramp and we have these little oscillations. That's a 1 degree oscillation. It's probably not that big a deal. The problem is that's cascaded to the hot oil temperature loop. The hot oil temperature loop during the same period is oscillating 10 degrees. So that means you're locally creating hot spots on the vessel walls of the reactor. I don't know the chemistry, but I know that the chemist probably would say, well, we gave you a set point of 4 whatever it is, 430 or whatever. We don't want it to be 440, and part of part of the reactor. So that's really a pretty significant deviation. So we need to get rid of that oscillation. So I actually took this data and imported it into the loop analysis tool to get a little better look at it, because it was a cascade loop. It's a little bit complicated. This is the loop analysis tool. It's really designed for continuous plants, but does have application here because during this step, we don't have any set point changes. It's really fairly continuous operation here. And the top part of this is a frequency response for the outer loop. And you can see there's the measured variable and the set point, and then the output of the controller is down below. Set point is a flat line. Set point didn't move. There's no frequency content. We have this big peak right here in the middle. I think it's around 30 minutes or so. All right. Well, that same peak causes the output to peak here. This output becomes a set point for this loop. So you can see this set point, the black line here, peaks, same place the temperature peaks. So the conclusion is that we need to tune the outer loop. The outer loop is totally driving the inner loop. The inner loop doesn't really have any instability on its own. So that's one action item that we'll have. All right, I'm going to switch gears now and look at some more of the discrete information, and we're going to look at some of the analysis capabilities of the tool. I'm going to step back here. In the first slide, I told you about the economics of advanced control projects. I want to just talk about that a little bit more here. We're tied to two things. First is quality control. There's really 4 ways that you can improve the economics by getting improved quality control. The first is somehow to keep the quality the same, but to decrease the cost. All right, you need some degrees of freedom to do that. This process doesn't really have any of that, to so to speak. A second method is to increase the yield at the same quality. That's usually something that's done in distillation. All right, so again, not very applicable here. Reduce off-spec losses. That's a situation where if you're off-spec, you throw the material away and burn it or send it to a landfill or something. Again, not the case here. And this last one is fairly rare, and that's where the value increases with quality. Usually it's not a continuous function. Usually you have 2 or 3 grades, and they're going to design the plant to make the highest quality grade. But sometimes what you'll find is you'll make a lower quality grade, and you'll have to decrease the value of a batch or of a production run. So this really is avoiding product degradation. That doesn't happen here ever either. So let's go on to production rate. Why is production rate important? Well, your fixed costs are held constant. You increase your throughput, so that means more revenue. So basically on a percentage or ratio basis, your economics look better, and you're making just more money for the shareholder. With a batch process, production rate really means cycle time. Here is a histogram that comes out of the tool that shows the different cycle times for the different steps. Well, you can see step 4 over here has a very long cycle time compared to the other cycle times. So we really need to focus on that. We can certainly clean up these a little bit, but this is where the money is going to be made. All right. So let's look at these rules applied specifically to the BASF reactor. Well, quality improvements. They hold every batch until all specs are met, so we can't get any better than what they do. All right. So the lab tests are repeated. Manual adjustments are made each time. They're lucky the reaction is reversible. They haven't locked in some bad bucket of material, but they can recover. So the penalty here really is that it increases the time. All right. So at the time we went to site, the plant was production rate limited on this product. I don't know if it still is or not.
We've got a lot more flexibility.
Yeah. All right. We did a good job. All right. So they had a long cycle time, and if we look at what the cycle times need to be, they had a 5-day work week times 24 hours a day. That gives us 120 hours of working time per week. If our batch time was 60 hours, we'd make 2 batches a week. If we could get that down to 40 hours, we could get 3 batches a week. I can tell you they were somewhere in between here when we came to site, and now they're below this threshold here. So they've gone from ability to make 2 to 3. So the real opportunity here at this plant was to reduce the the step times, and my animation clicked forward. So what I wanted to show you was the way we reduce step times is we reduce variance. We're never going to get a situation where we have only one bar here. All right? You're always going to have some spread. But we'd like to see this look like a normal distribution, because right now it does not look anything like a normal distribution there or here. And the reason this one is spread out is that you've got discrete times after lab tests that you add to the batch. So you've got a gap here, so that's probably one of these points where you failed the first lab test, so you add, I don't know, 6 hours, 10 hours, 12 hours. That's this next batch of numbers here. And if you fail again and you have to go to the third round of testing, then you're way out here at the edge of profitability, I think. So the tool has the ability to take in some of this discrete data and then correlate it with some KPIs that we calculate for the batch data. So in this case, I'm examining the effect on step 4, and I'm looking at one of the lab tests, and I'm looking at one of the process variables, the vacuum, because we know that affects the vacuum. The vacuum affects the acid number. And really what the vacuum does is it pulls more water out of the reactor, so that improves the acid number. So the reaction doesn't reverse as much, so it's pushing the reaction forward. So in the first plot here, I'm looking at this is all data from the lab entry sheet. All right, this is added time, so that's part of the recipe, and this is the acid number that comes from the lab. So when an operator gets an acid number test back, he looks at it, he says, okay, I have to add this much time. So if the acid number is out here, and if it's high, he's adding, it looks like 6 hours there. All right, so if the acid number is low, it looks like this is low enough that he actually made spec, so he didn't add any time. All right, that's what we get. So now let's look at the acid number related to the process value for vacuum. We can see that we get this kind of spread, but we have this general trend where the stronger the vacuum pulls, and the vacuum is given in PSIG here, so a negative number means more vacuum. So the more vacuum we have, the less time we spend, or the more vacuum we have, the better the acid number is. All right, I almost gave away the next slide. So what we're really interested here is, okay, this is a recipe number here, all right, and you can see it's not a straight line because there's other lab values that are affecting how much time the operator is adding here. All right, so it's a complicated situation. I would really need a multivariate analysis to really get that done. But then I need like a 3D or 4D plot, and this is a 2D screen. So let's see what happens when we look at real time against vacuum. All right, which is more important. Well, we get the same sort of slope. Again, we have a lot of scatter because the truth is, if you're working with real data, it's never really going to be pretty. But we can see that there's a general rule: the better the vacuum, the lower the total time was for step 4. All right. So the conclusion is investigate ways to improve vacuum, and they actually found a lot of ways without replacing the vacuum pump. They were innovative. I don't know much about the mechanical side. I'm not a mechanical engineer. I'm a chemie, so I understood the chemistry slides, but there were things they could do to the pump, and they got better vacuum, and they did have improvement over time. What's an interesting story is where these points came from. It's like, well, why didn't they operate down here all the time? Well, that actually kind of came from an accident, which we captured. So what we gained here was we gained a lot of confidence in the theory. All right. So we showed that yes, improving vacuum will decrease the drying time of the batch. All right. Now the PhDs would have said, we knew that. Well, they did, but maybe we didn't always trust them. So I want to step back here and talk about something called service port, which is really the big picture where all these tools are going and where they reside. They reside on my laptop, and I go from site to site, but we do have a plan to put them on a ABB supplied PC in your plant, all right? And there are different levels of sophistication that the tool has. The view level is just all these pretty plots that I showed you, all right, which are really valuable, and you can learn a lot from that. The scan level is where we start to do these calculations, all right? So I created a fingerprint report. It was based on view and scan. The next level, when we take it up to the next higher level, and we're not there yet with this product, is we want to take it to the track level, which means we're going to put this online and create some customized rules for analysis. And in case you don't have enough emails and enough text messages coming, we'll generate a few more for you. All right? That's very important to our marketing message, right? Or we could just send the message to the operator instead of the engineer. But, and we would have some sort of golden batch or ideal batch that would be running and plotting real time against the actual data. So the first thing we would see is when we had a condition like this, where we had this red line here, this batch had a long manual hold. There was probably something wrong in the process, something broke, or they ran out of material to add to the reactor. Or I didn't really investigate that. But the point here is that, okay, so step 2 got messed up, all right? But if we look at the deviation here, we would just keep alarming the operator over and over again that something's wrong if we just had a simple comparison to a golden batch of the actual running data. But if instead we use the tool to realign the data at each step, we can see that in this case I take step 3, which is this section, and step 5, which is that section. They're really quite the same. Once we get through that initial hold period, the batch, this batch from September 27th really look like all the other batches. So I think that's an interesting thing, is that this doesn't say that we don't necessarily alarm. This isn't talking about a new alarm. This is talking about suppressing alarm by being smart. All right. Next condition was there was a plant shutdown, and the transfer was recalibrated. And you can see this deviation here. This is calculated water flow going overhead. There's a condenser overhead. We can do an energy balance around that, so we kind of know how much water is created in the reaction. Operators watch this. It's important for them. If we would rescale this, we see that the delta jump is really much higher. So it really kind of threw the operators off more than it wasn't tied to any control. But the operators, I assume they watch this to make sure the extent of reaction has gone to completion before the next step would start. And I'm sure if they saw this somewhere up here and the next step was starting, they'd say, oh, something's wrong, I'm grabbing this, and we're going to do some manual control here and save it. So if you had the track situation, you would immediately become aware of this situation. I'm not sure how long it took the operators to complain. It probably was maybe only one batch. But one day. But we would have probably alarmed it in 1 hour. I'm not sure that the instrument guys would have got there any faster, but the point is that taking this kind of tool and putting it online can really, really provide some benefits. And the last example is this: the same shutdown. There was a what I called here a mechanical problem. It actually was probably an error in procedure. And what happened here is, if we look at the fractionator temperature, you can see it's much cooler, and it even affected the reactor here. If we look at the step 3 reactor temperature, you can see it took a lot longer to make temperature, right? So we were costing the plant money by slowing down production. A side benefit was we got all this data with this cool temperature, which helped vacuum, right? But it was affecting step 3 time. It was improving drying time, but it was, I think, hurting viscosity as well. So it affected chemistry in a different way. So now I think you guys can look away. You don't have to see this animation. I think it took 5 weeks to figure this out, because that's how many weeks of batches I have before the problem was disappeared. So.
Well, and we were also collecting OPC data manually and manually
right.
transmitting.
Oh, this was not online at all. And this was, if I would have done the report as soon as I saw this, I would have told them and they would have caught it. But the point here is there is a benefit for this tool to be online. So when people see this and say, well, why do we need this? Well, here's 3 examples that show for this tool, it's absolutely necessary and it would really be a wonderful tool to use.
Okay, and now we talk about the results. I think as you've seen from the various slides, there's a lot of work involved. Not just in putting together the data, getting the data. Alec and Ted put a lot of effort into putting together the OPC server in a virtual environment without any hardware, any additional hardware. So now we get to the results. And I want to say this I really think was a very difficult analysis. We were constantly making improvements at the site from our focus group. And I just kept on transmitting OPC files to Ted. And just kind of, well, we did this change, and just mark your data somehow, however you keep track of it, so that maybe that might help with cause and effect correlations that you might draw. And and definitely that I think contributed to some of the scatter that Ted saw. So as far as improvements, Ted talked a lot about evaluating more driving force on the oil loop. That's something for us to consider. Part of this is, this is not necessarily a hard reaction, but this is a batch reactor. It's a foot race, and we have to make it as best as we can, as fast as we can, and we have to evaluate and question some of our built-in assumptions. So that's one of them. And then observing that the batch cascade loop oscillation is there. We could see it on a trend possibly, but it's one of those things. Well, it's only 1 degree, and I think it's easy to lose track of these things when there's many issues going on. It's nice to find that does cause a 10-degree swing in our inner loop on the oil. That's not energy efficient. That's not cycle time efficient, and it's not really good for the equipment either. So, knowing that, we'll probably be looking to ABB to help us provide a solution for that. On the fractionator, the recommendation for temperature control, that it could use a feed forward. We were kind of suspecting that, and it's one of those things where there's a lot of different angles you can always attack, but which one is going to provide the biggest value? It's nice to have the tools that help back up some of our base assumptions. The fractionator temperature loop failure, that was definitely a case where we knew that there was a problem, but where do you look? It takes time, and then this is not the only thing we work on. So certainly having the tool that kind of tells us to home in on a certain part of the process, that is very value added. And a saturated transmitter, it totally went unnoticed until Ted notified us that hey, you might want to respan this. And I think ultimately something that's worth mentioning is that this is a very empirical process of analysis. Internally, BASF has its own advanced process control group, and they approach it from a theoretical standpoint. Well, okay, what reaction? They look at the reaction on the slides that I showed earlier, and well, there's reaction kinetics that govern how fast that should proceed, how much water you generate, how fast and when you generate it. Looking at the fractionator, this is the response that we would expect. And so from a very theoretical standpoint, it's always, I guess, very reassuring when your empirical and your theoretical do match up and come to the same general conclusions. That's a very good validation. And that told us, okay, we are pretty close to theoretical, so now we need to look at shaving off 5, 10, 15 minutes here or there, or whatever we can get to make it as good as we can, as fast as we can. And we did get the cycle time improvements from the plant group, and we will definitely be looking for ways to refine and hone our process, and this is exactly what we're going to be doing to get there. And just as a little bit related, as what Chuck indicated, as a final mention of benefits, we did have Ted and Alec plug into our system and take a kind of a health measurement of the system. And one of my counterparts kept on doing online configs, and it kept on crashing. Why is this happening? What am I doing wrong? The answer was nothing. You're doing what I would do. Maybe it was bad luck, but the reason it was crashing is because the fingerprint analysis of our BRC 100 modules determined that pretty much all of them, their NVRAM is overutilized. So we were right at the jagged edge, and so actually that has kind of delayed some of our improvement projects, because now we know if we put all those extra memory hog blocks into the BRC 100, we might not be able to bring the process back up. So and I've been in that situation before. That's not fun, but I think overall, it was a great partnership with ABB and BASF, and I think we've got a forward direction thanks to ABB's efforts and everybody's efforts here.